Hello, everybody. Thank you very much for your interest, and thank you, Dive, for inviting me over to report on our work on portfolio optimization. My name is Johannes Oberreuter. I'm working for a company called Reply. It's a consulting company doing IT services in general. I'm based in Munich, but we are represented all over the world. And we have been in the quantum domain for about a bit more than 5 years now. And since a while, I'm co-leading the quantum computing practice of Reply together with Marco Maganini. So as a consulting company, we work with our clients on various questions concerning quantum computing along the whole pipeline, along the whole value chain. And this time, we were very fortunate to have one of our long-standing clients, namely Raiffeisen Bank International, to ask us to assess together the potential of quantum computing, in particular the annealing technology, in this question of portfolio optimization. And we were so interested, and we found our results so worthwhile reporting, that we are putting out a paper together with these people you see over there. So I'm very grateful for, especially to Wolfgang Sakula and Jürgen Schiefer from Raiffeisen Bank International for the opportunity, and also to my colleagues Lucas Broni and Riccardo Aiolfi for collaboration on this project. So. Portfolio optimization. It's a good candidate for quantum annealing. I bet between 70 and 90% of the audience in the room or live in the live stream have optimized the portfolio. Can I have a quick show of hands? Who of you has optimized the portfolio with quantum computing? That's much less than I expect. Okay, we're all going to learn a lot. Of the people who showed hands, how many of you have checked that your solution actually lives up against state-of-the-art classical techniques? I see one hand, so let's please have a study group afterwards on portfolio optimization. Thank you very much. So I would like to still get us all to the same page and show why portfolio optimization is good for quantum annealing. I will explain a bit which choices we made, because I want to show that even with all the technology out there, smart choices can help you a lot to simplify the problem. I will show you several solution techniques, and will show you that you get better results with better techniques. And unfortunately, the world of constraints isn't always perfect, so we'll have to deal a bit about this. And finally, we'll have to see if a quantum computer could survive in business. So. What is portfolio optimization about? Well, it's actually quite simple. You have money and you want to earn more money. But in the process of earning more money, you don't want to lose so much, so you put some constraint on that. In some more detail, you have a given budget, and you want to, or you have to invest this budget completely. Either it's your own or it's the money of your client. And you can invest this budget in a given set of financial assets. You don't have all the world open to you, but given the product you're offering to your clients, you have a specific set of financial assets. And from these set of assets, you have a table which is reporting the average past returns and the average past volatility, a variance of the time series of the data. This is just how, in classic portfolio theory, the risk is defined. I'm not saying this is a good way to invest your money, but this is how it is defined. And the whole thing is called Markowitz portfolio optimization. It's a classical thing of the trade. The goal is, of course, maximize your expected returns. And on the other hand, set yourself a risk class, how much money you're able to lose along the way or to dip below. So meaning keep the expected volatility at bay, given the past data you have. So this is an optimization problem. You have to see how much of your money you want to put into which asset. In principle, it's not difficult to do. It becomes difficult to do once you impose constraints on the problem. That's where the whole problem lives and can be interesting and can be NP hard. Raiffeisen Bank International is doing this process several times a day. It's happening all the time. It's one of their core businesses. That's why they were interested in it. And they had a real-world data set to provide to us in order to play with it and look at it. And in this real-world data set, the one that we chose, three main asset classes are present. One of them is equity, fixed income, and money market. And then, to my surprise, to be honest, a typical client portfolio doesn't consist of so many assets, between 9 and 11. So that's what they usually want to optimize. However, you have to impose various constraints, be it because this is how you design your product, or be it because you have regulators who decide what you can do, what you can sell, what you can combine in terms of financial instruments. So let's put this into mathematics. The stuff here on the lower left is for the formally minded of you. Don't get confused. It's actually quite simple. You want to optimize and maximize the return of your assets. And there are certain constraints. Volatility constraint we already talked about. That's a quadratic constraint. You have to know your variance. You have another constraint, which is the weight constraint. That means please invest all of your money. Don't run away with it. So that means W is the weight. So all of the weight should be the weights of the asset should sum up to 100% or to 1. And then you have a number of linear constraints. The linear constraints is where it really gets interesting. So in practice, one of the constraints which is really important is that you have lower and upper bounds on what you can invest into a specific asset. And you have multi-asset constraints which put bounds on, for instance, a group of assets, an asset class, or on the relative investment between the groups. So we had all these constraints tabulated, and these are the constraints we want and we need to impose in the problem. So we have heard just in the previous talk, or one of the previous talks, how to do this in a Cubo formulation. We all know how Cubo works. I'm giving you another formulation up here, or another impression of the formulation. And in the plain vanilla Cubo approach, the axes are the binary variables, right? You have to put in a binary variable there, which means you make a choice of some sort, as we have just heard before. And the Cubo problem is now to find the minimum or to optimize this with respect to finding the best configuration of binary variables such that your objective function, which I'm giving you up there, is minimized, corresponding to our returns of the portfolio being maximized. Now, you have to, on the one hand, discretize your continuous variables somehow if you want to express it in terms of binary variables. Mind you that we did these experiments before I believe CQM was actually offering to use continuous variables. That's the one reason why we do this, or why we are discretizing our portfolio, or our variables. The other reason why we have to do this is because we wanted to benchmark CQM against other solvers as well. So this is why we are actually discretizing our continuous variables. On the other hand, as you know, it's an unconstrained formulation, so you have to include your constraints as appropriate costs, as appropriate penalty on your objective function with appropriate Lagrange multipliers. So we thought about this a lot, how we would like to do this. And in the end, we decided to discretize our solution space, or our weights, given in a binary representation, up to a given granularity. Now, this granularity has, of course, one problem. You can increase the granularity, which will give you better results. You have a better approximation of your continuous variables. But it will also demand more resources. You need more qubits in order to represent your portfolio, which can or cannot be a problem, depending on how big your portfolio is, and if you want to put it on a quantum computer, of course. Second thing which we realized is that we can leverage actually one of the constraints in order to save resources. As I told you before, there is a constraint giving a lower and an upper bound on the money, the budget you can invest into a single constraint. That means below this threshold and above the threshold should never happen, meaning you can actually focus your attention, focus the attention of the computer onto this range which you actually can invest on. That has two advantages. One advantage is your granularity takes you much further. You need less of a granularity in order to achieve a higher accuracy representing your continuous variable. Because essentially, you're limiting the space. Rather than discretizing anything between 0 and 100%, you only have to discretize this part of the percentage or of the weight of this particular asset. By the way, in our case, this spread was the same for all the assets, but that was it's just a detail of our implementation. The second thing is you already automatically, if you do this, satisfy the min-max constraint. You don't have, it will by construction never happen that you violate it, and you're saving one constraint per asset, which you do not have to impose as a Lagrange multiplier, which you don't burden your QPU with. So this is automatically satisfied, and you're already done with it. So this is why we decided to go with this, saving resources on the one hand, and saving effort in modeling the constraint on the other hand. But there are still constraints left, and there are still terms left in the objective function which we need to model. So first of all, of course, is the maximization of the returns. This is the point of the whole exercise. So this is what we need to maximize as the first term. Second one is the weights constraint. Everything has to be invested. That's an equality constraint. So far, so good. That's easy to implement. Third are all the linear constraints which remain, meaning combining various assets in one class, putting bounds on how much you can put into one asset class, and so forth. These are typically inequality constraints of some sort, or smaller equals constraints, bigger equals constraints. So this is something you can also still implement quite nicely, because you have an equation, you want to minimize, or you want to get closer to a specific threshold. So usually what you do is you take your boundary, you take a difference, you want it to be a nicely shaped potential, you just square it. That's how you go about it, right? You want to find the minimum of this, you square it, you are sure that you're always driven to the minimum. That's a good way of approaching this. But then, quite fundamentally, if you put out a product, you also say what the risk class of this product is. So in classical portfolio optimization, this is just a number. It's a fixed threshold. You just put it somewhere. Here, in our case, it is a constraint. Now, volatility is variance, and variance contains the standard deviation. The standard deviation is something which contains your random variables in a squared fashion. So all of our binary variables which you have been using are in there already squared. Now you want to minimize it, so you want to put this to a specific threshold, meaning you have to square it again. If you square a square, what you end up is a quartic potential. Ouch. That's too much for a quadratic system. So there are various ways you can do, or you can go about that. You can either just linearize the constraint, for instance. That would have been one possibility. Or the way we decided to go about it is we would just put it as a constraint to be minimized as well. So we just did not put the threshold. We just said, make this minimal, but we didn't take it so seriously. So we had this extra Lagrange multiplier over there, which helps you to play a little bit with it and make sure that you don't have to achieve the actual minimum. So this is one way in which you can play with such a constraint if you want to impose it in a quadratic model. Mind you, all of these numbers have to come from somewhere. You have to determine them when you set up your model and when you have to impose all of these constraints by hand. There are various ways you can do it. You can just pull them out of your hat. You can use Bayesian optimization for that. You can do some sort of a grid search, but this will cost you time. And this is a significant amount of time and amount of modeling effort which you put in there. And of course, there are interdependencies, so you really have to make sure to get that right. Otherwise, your model might not give you the optimal of what you're actually looking for. So this is how we set up our model. And then the goal of the whole exercise was to benchmark how various solvers, how various approaches to get the results from this objective function are competing against each other. So we are trying different ways to solve the QUBO. We are getting the statistics, and we are comparing those results with each other and with the classical result. First of all, we decided to go with QBSolve as a classically heuristic benchmark. We went with the hybrid binary quadratic model from D-Wave, both of which require careful tuning of these Lagrange multipliers up there. And finally, we went with this new hybrid constraint quadratic model from D-Wave, which does not impose on you to tune the Lagrange multipliers. On the other hand, you don't know exactly what is happening there. with the setup we have for the QBSolve and for BQM, we have full control over the model. We understand very well what's happening. In hybrid CQM, we don't quite understand that, but we save a lot of time in modeling. So let's see what's happening. First of all, so what I want to present to you is a comparison of the results of the three solvers. And then I want to go with various granularities. I want to see if adding more qubits, if adding more refinedness to our weights will improve the results. So first of all, I'm not sure if you can see the point clouds, but I will walk you through the plots. Don't worry too much. This is a representation of the solutions we obtained. We were sampling the solutions, obviously, and this is what we obtained. On this axis, we have the volatility of the resulting portfolio, and on this axis, we have the expected return of the resulting portfolio. And you have a cross here. So this one gives the classical result of the return, and this is the volatility threshold imposed by the actual problem. Now, how do we arrive at this line? There is a system in place at the bank. It's using, we already mentioned that CPLEX, IBM, and we believe that for the given set of assets, for the given portfolio size, that what the classical system determines is actually the real optimum. So that is something you cannot really beat. So you would actually like to get as close as possible to this point. So what do we find? We find a point cloud here of solutions. You already see that some of the solutions are exceeding the volatility admitted. So those are solutions you cannot use. And you see that as a sanity check, it kind of makes sense that you have the tendency going from lower left to upper right, meaning that if you have a portfolio with higher volatility, higher risk, you're rewarded with higher returns. So kind of this sanity check makes sense in general as a portfolio. You also see or might not see that there are points in two colors. One is with constraints violated and one is without constraints violated. You see this over there. So let's see, this is for QBSolve. Let's see what happens if we add a hybrid method. What you see is the tendency is still the same. We are still approaching, or we are still around the point where we want to be classically. You see that the variance is much lower as compared to QBSolve, so that's a good thing. The solutions seem to be more focused. It seems to be seems to make more sense. There are still some violations of constraints given our construction, but that seems to be a step forward, definitely. Now, what happens if we do not manually add the constraints? This is quite interesting because the shape of the resulting point cloud is now changing. It doesn't show this elongated form anymore. Again, variance is reduced. That's very nice. We seem to be much better at satisfying the constraints. So you see the number of points above the volatility threshold is reduced. And we are approaching, so ideally we would like to get a bit more still to the right with respect to the return. So far so good. That's just a visualization of the results we got, as a point cloud. No evaluation yet. So what happens if we now increase the granularity? Well, for QBSolve, it's not so clear. Not much seems to happen, right? Variance is still quite big. Constraints are still violated, maybe a bit less anyway. Doesn't seem to do much. So 10 qubits per asset seems to be a bit of the sweet spot. For hybrid BQM, it even seems to become worse, which is a bit surprising to me. But it's something which we see more often. Increasing the solution space can make it easier to satisfy constraints, can make it easier to find optimal solutions, but it also demands a better search algorithm or a better search, more search efforts because you have a vastly larger solution space. So it happened, we have seen this with other projects as well, that your solution might actually not become better, although you provide a larger space for solution to the algorithm. Now, look at what happens if you do the same for hybrid CQM. Isn't that amazing? It seems to be really all concentrated on the almost optimal point. So this was really a surprise to me. I really enjoyed to see this. This is an amazing step forward for the solution quality. Now, This is just a visuals. It doesn't mean that you can use this in business or that it gives you a real advantage in business. Let's see how this is happening. That is unfortunate because there used to be a histogram, actually, of all the solutions, which seems to have been lost in translation. But what you still see on the slide is the averages we got. That is the dashed line here. I'm sorry for the histogram not being visible. But the average, the mean of the result is not necessarily what tells you most, because from all the solutions you sample, you will not take the medium solution or an average solution. You will take the one solution which gives you the best return at the best volatility. What I didn't tell you, due to my surprise, is what I'm actually plotting here. On the left side, we are plotting the distribution of the objectives, meaning the return. In the middle, I'm looking at the volatilities, and at the right, I'm looking at the Sharpe ratio. The Sharpe ratio is essentially the objective divided by the volatility, which is an important quantity for us to look at because we are not fixing the volatility. So that means we might have a higher or lower volatility, but still getting higher or lower returns. So this is a quantity which allows you to check how good your portfolio is performing given the volatility you're actually having, compare volatility normalized. So I'm really sorry about the histograms not showing up, but the dashed line would be the medium, whereas the solid lines are the best permissible portfolio, meaning that is the portfolio which is satisfying all the constraints, but still giving you the best return for the volatility given. So the different colors in here are QB-Solv, blue, hybrid BQM in orange, and hybrid CQM in green. So what you can see with 10 variables that they are all kind of close given the business relevant portfolio. But in terms of the Sharpe ratio, the BQM, the orange one, seems to be slightly or is slightly better than CQM. Now, that is a bit surprising given the plot I showed you just before. But mind you, you just need one lucky shot. If you have one shot in a specific solution strategy, which is the best, you will just take that one, and that can very well be better than what you expect given the whole ensemble performance. Is that an advantage? Yes, it is. However, you have to put in a lot of modeling effort in order to get there. BQM takes you a lot of time to get the constraints right. You have to discard a lot of your solutions. So that is some trade-off you need to consider. Let's have a look at what happens if we use 20 variables per weight. Well, the cards seem to change a bit. Now, CQM seems to be better in terms of the Sharpe ratio than BQM for the best permissible portfolio, given presumably that the BQM result, in our case, in our approach, became actually worse in this case. Okay. Let's jump over this one. So you have seen that none of our results actually, we cannot beat the classical computer because we are already there, right? We already know what the optimal result is. But the question is there potentially a point where it becomes really, really difficult to optimize a portfolio classically? So we were interested in if we can scale up to, for instance, a large portfolio with 499 assets. What we saw here is we took again, objectives, volatilities, and Sharpe ratios. So you see that, again, comparing 10 assets in blue and 499 assets in orange, that it seems that the Sharpe ratios are, the objectives are on par. They're pretty the same, and the Sharpe ratios don't differ so much. So this is something which really works. So you can scale up to 499 assets in a portfolio, but that's something which is still not going to be a problem for the classical solver. Now, unfortunately, all of these histograms got lost in transferring the slides, apparently. So let me just say a few things globally here. There are a few, in general, what we see is that CQM violates far less constraints than our construction in QBSolve and BQM does. In fact, from all the solutions we generated with CQM, none of them violated any constraints. So that was very good. We saw in particular that benchmarking CQM for various granularities, which we have examined 4, 10, 20, and 40, that in general we are not getting that having higher granularity does not generally help. And we have seen in scaling up to 499 assets that CQM is providing you valid results, while QBSolve, which is the other solver with which we got there, does actually not give you any permissible results. So in this sense, CQM does a very good job. Good job, D-Wave. Thank you for providing this. My downs, we have colors. Amazing. Thank you very much. But I'm out of time. So you can confirm that what I just said is indeed true, given these colors. Let me wrap it up. So hybrid solvers do improve the results which we find. In particular, hybrid CQM is improving the solution quality. In a known optimization setup where we know the optimum, it can be approximated very well. So quantum computing is definitely an alternative to solve this problem. Scaling to a large portfolio, which might be interesting in order to get a quantum advantage, which we haven't manifested here, unsurprisingly we haven't manifested it, is doable and is possible. But close attention must be given to constraint fulfillment, because this is really bad if your solution violates constraints. So what we now do is we are looking for a quantum sweet spot that might be scaling up the number of assets. I don't believe this is really the way to go. I think we'd rather have to find new sources of complexity of the problem, for instance, having more complex constraints or different constraints, which we see make it much, much more difficult to solve the problem. Thank you very much for your attention, and I'm happy to take any questions. I'm on Chime or afterwards in the break. Thank you very much.